Hey folks, final two videos for Unit 5. In this one we introduce Newton's second law for rotation, which is pretty simple, talk about problem solving and general use, and then next video we do some problems. So here we go. Newton's second law for rotation is probably something that you can guess based on what we've done in class and what you've seen in the videos, but to make it explicit, in Unit 2 we talked about linear acceleration and how it is proportional to the net force on a system, and it is inversely proportional to mass. In other words, acceleration of a system equals the net force divided by the mass. So we've learned analogs for acceleration, force, and mass in this unit, and so now we're going to put them all together, and we can say angular acceleration, which is alpha, is proportional to, and so the thing that's going to cause a change in angular velocity is not a net force, but a net torque. And inverse and proportional to 1 over iota. In other words, the thing that resists a change in angular velocity is the rotational inertia of the system. And so angular acceleration equals net torque over rotational inertia. And so this is Newton's second law for rotation. The way that we're going to use it, and you'll see me use it in class, is net torque equals I alpha, although conceptually speaking, this expression solved for angular acceleration is more useful because you have the reason for angular acceleration and the reason for a reduction in angular acceleration, so net torque and rotational inertia. So that's kind of it. We haven't introduced any new quantities, but now we're putting them together in a way that's very familiar. The problem solving for Newton's second law for rotation is more complex because torque and rotational inertia are more complex, and also any rotational motion might also incorporate linear motion. So this law applies to both point masses circling an axis and extended objects rotating around an axis. So you may find yourself having to calculate rotational inertia for point masses or dealing with expressions for extended objects. We have a very familiar approach for using Newton's second law, and that is to begin with a force diagram for all objects. One of the very popular question formats for rotation in AP Physics 1 is a mass hanging from a pulley. And so when you do a force diagram, you would typically do one for the pulley, which is the object that is rotating, and then the mass separately, which is the object that is accelerating with in a straight line. The next thing is to kind of take care of like the basics here. So you have to manage the positive and negative directions. And you also have to identify the axis of rotation. So these are things that sometimes the problem tells you exactly what to do, and often it leaves it up to you to interpret which way is positive and which axis is the axis of rotation. You would want to use then expressions for, and this is where the list gets kind of big. So we have net torque, and so that's the sum of the torque due to every force. So keep in mind torque equals RF sine theta. Expressions for rotational inertia, that's either going to be the sum of m times r squared or a derived expression. And also you could use the parallel axis for that. And then even, especially when you have both linear and rotational motion in a situation, you might need to have an expression for angular acceleration. So keep in mind this relationship between linear and angular acceleration. Again, the pulley is the major item in physics where linear and angular rotation coexist because the string has a linear acceleration but the pulley itself has an angular acceleration. And again, like you've seen in this course, when we use Newton's second law, there's no strict formula for how you're going to do things, but these are just the major tools that you have access to. So we'll do a couple of problems in the next video that'll get you started, and we'll do lots of practice in class.